Okay, class, this is a lecture on VESPR and molecular geometry. This can get slightly confusing, so I suggest utilizing your models as we talk about this and trying to visualize the process. A huge portion of this field in this chapter is being able to visualize the different electron domains. So that's the key. That's what we're trying to teach here in a few different terms. So, first off, let's talk about some old Lewis structures. So if we have an element A with one valence electron, we draw a Lewis structure. We draw the one valence electron here. And if we have an element with two valence shell electrons, we'll draw that something like this. VSE standing for valence shell electrons. And 3, we do one on each side, 4, one on each corner, and this is our last piece of unpaired valence shell electrons. Once we get to 5, they start to become paired. Now, as we learned in the last chapter, or a few chapters ago, this is stable. All right, we're looking at something that looks kind of like this in a box, and this is stable. So that's interesting. Keep that in mind. If we do 6 valence shell electrons, it usually ends up with 2 stable pairs and then 2 unstable electrons. 7, now we're talking. Now we have 3 stable pairs and 1 unpaired. So this one is highly reactive because it's looking to bond this one right here, making that one very reactive, just looking to make a bond. And then finally, with 8 valence shell electrons, we have 4 full pairs. And this is our normal noble gas configuration. So that's a quick review. So now the next step of the Lewis structure is not so much how many valence shell electrons there are, but now here's the key. Let me zoom in. Valence shell electrons can move in and out of an electron domain. And this is equal to the bonding pattern or the chemical and physical properties. So if we have a compound that has a certain physical or chemical property, that in turn comes from the bonding patterns that it creates, which in turn comes from the movement of valence shell electrons in and out of electron domains. So what's the difference between the valence shell electron and an electron domain? An electron domain is an area where an electron could be. Now, could be as in like it's in the subjective tense, knowing that it hasn't quite happened yet. Now, if 2 electrons happen to line up in the same domain, now we have a chemical bond. So we talked these, another word that we'll use is electron cloud. That makes it a little bit easier. It's just this idea of this is where an electron could be, and if it's paired there, it can make a chemical bond. That's the big key. So take a moment, copy this down, pause the video if you need to, and we're going to go on to the next part. So VESPR is more or less the geometry of electron domains. That's more or less what we're talking about. So now this is for like single central atoms. Another So let's see here. We have a few that are very, very important. If you have an element, A, and it has one valence shell electron, like say a hydrogen, that it can be in a linear pattern. Well, that also refers to if it has two that can bond. Now these little cloud things, let me draw those in different color actually. Might make it a little bit easier. Here are the electron domains. And notice this creates a linear pattern, as in like it's straight right next to each other, which is very interesting, which is very useful. And if we have more than these two, if we have three, you would have here 3 valence shell electrons, and then our electron domains would have 3 different clouds here. Now this is in a very interesting geometry, and we call this trigonal planar. Trigonal as in triangle, in gray, I'll just, here's our triangle. Trigonal is in triangle, as in 3, and planar is it's all in the same plane. There's no z axis. It's all in the x and y plane, so it's all in one level. And the reason why they're all in one level is that we have a repulsion between these negatively charged electron domains. So that is a key to VESPR theory, is that because there's electrons that are negative in the electron domains, the domains are all negative, so they all repel each other, which is something that we know. Opposites attract, and similar charges repel each other every time. So that's nothing new. And so each of these repel each other the same amount, creating the same angle between, and the angle is 120 degrees between each of the electron domains. Cool, so that's 3 valence electrons. Now if we have 4 valence electrons, we would have at this point 4 electron domains. Now, because they are going to repel each other as well, they're actually going to push themselves into a very special shape. And this is probably the key to one of these chapters, is the shape tetrahedral. That's terrible. Let me rewrite that. Tetrahedral is that like New Mexico goat head shape. It looks like if you have an element, you have these two are in the same plane, as in like they're in the same plane as the board. This one that's darkened means that it's coming out toward the screen, and this one that's like kind of dotted or dashed is going behind the screen. So and this angle between each one of them is 109.5 degrees against all of them. They're all the same angle apart. And so you can imagine like these balloons that push each other away, they're not perfectly perpendicular, they're a little bit larger because they're fitting in a sphere, 3-dimensional shape. And because of that, we have this tetrahedral geometry, very strong, very stable. This is why carbon is carbon. It can make so many different bonds and be one of the main ingredients in life on planet Earth, is because of this tetrahedral shape. Cool, and that has 4 valence electrons. Let's go to the next one. Next one is if we have an atom and we have 5 valence electrons. Now, if we draw in our electron domains, we could have 5 of those as well. Now, these are all going to push each other apart also. Push this way, push this way, push that way. And as they push each other apart, think of the balloons, they end up in a really interesting position. You will have, let's put it in black. If we have our element A, we will end up having these 3 domains on the same plane in this trigonal planar, which let me draw that triangle just to show. So we have 3 of the 5 in this trigonal planar geometry, this triangle. And then we'll have 2 more, one on top and one on bottom. So if I'm going to draw in my electron clouds. Cool. Now let's go back and draw in that triangle. So we have a triangle here, but we also have this triangle that goes up, kind of like a pyramid. But we just don't have one pyramid on top, we have 2 pyramids. And this last one goes behind. Let me draw that a little bit better. And this one just goes behind to that one, ish. That was also terrible. So we have what we consider here trigonal bipyramidal. Bi as in 2, and we have a pyramid on top, and we have a pyramid on bottom. So we have one pyramid up here, and we have one pyramid down here. And they're kind of mirrored images of each other. So when we have 5 electron domains, we are in a trigonal, triangle, bipyramidal geometry. Trigonal, bi as in 2, pyramid as in pyramidal. So that's really cool. Now what happens if we have 6? We have our element here. Now let me draw in some electron clouds, aka electron domains. Now, very similar to before, we have, instead of a triangle, we have a square. But we also have these ones on top. So we have what we consider a square bipyramidal. But we have a short term for that, and if we count every face on each of the pyramids, on the top pyramid, let me just redraw that out here. If I count each face, I have 1, 2, 3, 4 faces on top, and I have 2 of those, and that's 8 total faces. And so that's where we get the name octahedral. So instead of saying square bipyramidal, we say octahedral. So those are the VESPR domains. Take a look, understand which ones that you need to know all of them, and you need to know which ones you know, which ones you need to memorize. So there's 5 main ones for VESPR. Oh my goodness. So VESPR has 5 main domains that you need to know. Linear, trigonal, planar, tetrahedral, trigonal bipyramidal, and octahedral. And we have a pneumatic that would help with this. If you're into that, let's go blue. Linda tries Tetris triangles once. Linda tries Tetris triangles once. Linear, trigonal, planar, tetrahedral, trigonal bipyramidal, octahedral. Linda tries Tetris triangles once. If you want to make up your own, go right ahead. And one last thing I'm going to talk about that we have to just remember for our next section, next section of this chapter, is VESPR, primarily for the base or the central atom. Molecular geometry is for the rest of it. So for the base and the central atom, we're talking about these 5 words, these 5 geometries, these shapes. And for everything else, we'll talk about later on the next video. Okay, cool. Let me know if you have any questions. Email me, and we'll go from there. Have a great day.